This video, we're going to go through chapter 10, section 2, estimating a population mean. So in the last section, we went through finding the value for T star for the T distribution. Remember that we use the T distribution when we're estimating the true mean as opposed to the true proportion of a data set. And then we will actually calculate the intervals and then analyze an interval for this problem. So a teacher wants to estimate the mean height of seniors who attend a large high school. He randomly selects 35 students from the school and records the heights in inches of these students. The average height is 64.7 inches with the standard deviation of 4.1 inches. Determine the 90% confidence interval for the true mean height of the students at the school. So the first step is to state the confidence interval, which is actually in our question. So we're doing the 90% confidence interval for mu equals the true mean height of students at the school. So then we want to name the inference procedure that we will use for this lesson. It is the one sample T interval for mu. So remember that we had a one sample Z interval for P. So if we're looking for population proportion, it's a Z interval. And then we know how many samples we have. We'll look at two sample ones later on in this unit. So checking the conditions, it must be random. So he randomly selects, tells us that it is random. Remember that 10%, we have to check if something is taken without replacement. And so this is not without replacement. Oops. Another way that we can do this is that 35 is likely less than 10% of a large high school. Okay, so if I think about a large high school, that number should be a lot larger than 350, right? Because 350 would be 35 is 10% of 350. So large high school, definitely more than 350 students. So we're gonna say that that one is met. And then the last one is the normal or large sample. So remember, we're looking for, it says that the heights are approximately normal or normally distributed, or we can have the data and we can see that it's not like really skewed or have any outliers. This one meets this requirement because of the sample size, because 35 is greater than or equal to 30. So it meets that requirement. So since we've met all three conditions, we're going to do the calculations. So the formula for the interval of a one sample T interval for the mean mu is we take X bar. Remember, X bar is our sample mean. So the sample mean is the average height. So this is X bar is 64.7. The sample standard deviation is S sub X, which is 4.1. N is our sample size, which we already said was 35. Remember that the degrees of freedom is 35 minus 1. Our sample minus 1 is 34. That gives us the T star value. So remember that we always round down. So rounding down, sorry, I can't, I'm trying to change colors here. So rounding down here would be 30 because 34 is not on there. And then remember that we're looking at a 90% confidence interval. So we're going to use the T table to determine where 90 and 30 meet. And so that's 1.697. So that means that T star is 1.697. So we need to use X bar, T star, S sub X, and N in the formula to determine our interval. So we're going to take 64.7 plus or minus T star, which was 1.697, times our sample standard deviation, 4.1, divided by the square root of our sample size, which was 35. So we're going to take the square root of 35 in our denominator. So we're going to calculate these values. So if I calculate 1.697 times 4.1 divided by the square root of 35, that piece is going to give me 1.2. So that means that I'm going to take 64.7 plus or minus 1.2 to get my interval. Okay, so what that means is my first value, my lower bound, is going to be the difference. My upper bound is going to be the sum. So my lower bound is going to be 64.7 minus 1.2. And my upper bound is going to be 64.7 plus 1.2. So if I subtract and then add those two numbers together, my interval goes from 63.5 inches to 65.9 inches. So now that we have that interval, our conclusion is that the teacher in the problem can be 90% confident that the interval from 63.5 inches to 65.9 inches captures the true mean height of, I'm just going to say of student. Okay. So I will need to answer questions about an interval in some cases. So that's my interpretation. The teacher can be 90% confident that the true mean is somewhere between 63.5 and 65.9. Okay. It doesn't mean that's in the middle. It could be one of those numbers. It could be something close to those numbers. It could be in the middle, anywhere. So is it plausible the true mean of seniors may be 63 inches? So really all that you're asking yourself is 63 between 63.5 and 65.9. Okay. And so the answer here is no. Because 63 is not in the interval. Okay, so I'm checking to see if that number is in the interval, then it would be plausible. Is there evidence that the true mean height of seniors is less than 66 inches? So what I'm doing is I'm looking at the entire interval and asking myself, is 63.5 less than 66? Yes. Is 65.9 less than 66? Yes. So that means that this is plausible because the entire interval is less than 66 inches. So if I'm asked about a specific value, and if that's possible to be the true mean, then I'm just looking, is it between the two values that I have? If it is, then it's yes. If it isn't, then it's no. If I'm looking at an inequality, I have to have the entire interval to make that inequality correct. So if it was, is the true mean height of seniors more than 64 inches, that would be incorrect because there's values less than 64 within the interval. So that's what you're looking at for an inequality. It's a little more complicated. The very last thing that we'll talk about is having to do with changing values. But first, let's look at a different example where we're checking conditions a little bit differently. So in this problem, if I'm checking conditions, I'm looking for the word random for random. So I have varsity swimmer at a large high school wants to estimate the amount of time and hours on average athletes at school train for practice each day. The swimmer randomly selects, so randomly, 10 members of her swim team and asks them how many hours they typically train or practice. The data is used to construct a confidence interval to estimate the true mean number of hours. Okay, so the 10% condition cannot be verified because it's not known how many seniors in the population versus the student selected random sample 10 is less than 10% of the population of athletes. The graph of the data shows no skewness or outliers. Okay, so if we look at the data, if it's a large high school, then our 10% is likely to be 10% of the population. And so we want to look at the data itself. So if I check my data on a dot plot, so if I have one value at 0.5, I have 3 values at 1, I have 3 values at 2, I have 2 values at 2.5. Now that looks pretty symmetric, but then I have this value at 5, which looks to be an outlier. Okay, so that means that this is incorrect because the graph of the data shows skewness. Okay, so because I have that outlier, this is not going to be something that we can use the test for. The last piece of this is talking about something that we addressed last unit, which is how to decrease the margin of error. So we can decrease the margin of error by decreasing the confidence level or increasing the sample size. So this is still true in terms of a t-distribution. So as the margin of error increases, the confidence level increases. As the confidence level increases, so does the value of t star, which increases the margin of error. Okay, so that's why that's working. The margin of error decreases as n increases. Remember, this is our sample size. The margin of error would decrease if the standard deviation would decrease. The margin of error would increase if the standard deviation would increase. So these happen proportionally. Notice that we can choose both the confidence level and the sample size, but we have no control over the value of the standard deviation because it's randomly selected. So if I'm thinking about this, how does the confidence level affect the margin of error? So the increase in the confidence level increases the margin of error. Decrease in the confidence level decreases the margin of error. So those work in the same direction. In opposite directions are the sample size. So as I increase the sample size, that's going to decrease the margin of error. And as I decrease the sample size, that's going to increase my margin of error. Okay, so bigger sample has a smaller margin of error. So this is the same as what we learned in the last unit. The only thing that is new here is that the margin of error would decrease if the sample standard deviation would decrease, and it would increase if the sample standard deviation would increase.